Assalamualaikum warahmatullahi wabarakatuh. So welcome again to another series of vector analysis. Today's class we're going to cover scalar field and vector field and Cartesian, cylindrical and spherical coordinate system. Scalar and vector field. What does it mean by field? A field is a region of space in which a given effect exists. So, scalar field is an assignment of a magnitude to each point in a subset of a space, while vector field is an assignment of a vector which includes both magnitude and direction to each point in a subset of a space. One of the examples of scalar field is Mount Fuji. Mount Fuji has an elevation of 3,776 meters, which is its magnitude. It doesn't have a direction. Also, Mount Kinabalu, it has an elevation or a magnitude of 4,096 meters. Examples for vector field include Hurricane Katrina, because this hurricane consists of magnitude and also direction because it is moving. Some other examples for scalar is world average temperature, and for vector field we have ocean current because ocean current have both magnitude and direction, while world average temperature only have the magnitude. Coordinate system. So in coordinate system we have three kinds. The first one is Cartesian, second one is spherical, and third one is cylindrical. So for Cartesian coordinate system, we have a point P in this case. So point P should be here. Point P consists of x1, y1 and z1. So the magnitude of point P is A, which consists of ax hat plus ayy hat plus az z hat, where all the x, y, z hat is the base vector. So how to find out the length, the surface, and also the volume? So you have to make sure that for each of these coordinate system, you have to identify what is the length, the surface area, and also the volume. So questions will be based on this. So first, the differential length, dl. So dl for Cartesian is equal to x hat dx plus y hat dy plus z hat dz. For the differential surface area, you will have dsx equal to x hat dy dz. For dsy, you will have y hat dx dz. And for dsz, that will be equal to z hat dx dy. So S here stands for surface, okay? And then L here stands for length. And finally, we have the differential volume, which is denoted by V, dV. So dV for Cartesian is equal to dx, dy, and dz. Next, we move on to cylindrical coordinate system. So cylindrical coordinate system involve point P, which is include of R, the radius, and then the phi, which is the degree here, and Z, which is the z-axis. Okay, so point P would be around here and give you the magnitude vector of A. So A consists of AR R hat plus A phi hat plus AZ Z hat. So instead of have X, Y, Z, now for a cylindrical you will have R phi, and also z. So r, phi, and z hat is the base vector for the vector in cylindrical coordinate system. Now you have to find out the three things, which is the length, the surface area, and also the volume. So this depends on the question that is being asked to you. So whether the question asks you to find out the length, the surface area, or the volume, or even all three. Okay, so here you have the differential length for cylindrical coordinate system, which equal to r hat dr plus phi hat r d phi plus z hat dz. So notice that you have an extra r here for the phi. Now for the differential surface area, you will find dsr, ds phi, and also dsz. So dsr is equal to r hat r d phi dz. For ds phi, that will be equal to phi hat dr dz. And for dsz, equal to z hat r dr d phi. So again, the S here stands for surface area. So when you have dsr, ds phi, and dsz, straight away you can identify that this is a cylindrical coordinate system because you have r, phi, and z instead of x, y, z in Cartesian coordinate system. Next, you have the differential volume. So for dV in cylindrical coordinate system, this is equal to r dr d phi dz. Next is the spherical coordinate system. So spherical coordinate system looks like this, and you have point P, which is here. Point P consists of r1, theta 1, and phi 1. So when you see r, the big R, theta, and phi, this would refer to spherical coordinate system. So vector for spherical is equal to AR r hat plus A theta theta hat plus A phi phi hat. Now the differential length dl for spherical is equal to r hat dr plus theta hat r d theta plus phi hat r sine theta d phi. For the differential surface area, you will have dsr, ds theta, and also ds phi. And finally, for differential volume, you will have dV is equal to r squared sine theta dr d theta d phi. So all the equations for differential length, differential surface area, and differential volume for all three coordinate systems, Cartesian, cylindrical, and spherical, would be in this table and to use. So here you can see that we have the coordinate variables. Okay, so for Cartesian, when you see x, y, z, you know straight away it is Cartesian. So cylindrical, you have r, phi, and z. Spherical, you have capital R, theta, and phi. And then you have the magnitude for all three, the position vector, the base vector properties, the dot product A dot B, the cross product A cross B, the differential length, the differential surface area, and the differential volume. So dl, ds, and dv will be given in this table. Now, relation between the three coordinate system. So you can actually change from Cartesian to cylindrical or the other way around, or from Cartesian to spherical, or vice versa, or from spherical to cylindrical, or vice versa. So in this case, you have Cartesian to cylindrical or from cylindrical to Cartesian. In this case, you are changing from Cartesian to spherical or from spherical to Cartesian. So whenever you want to convert the coordinates, which is from xyz to r phi z, or from r phi z to r theta phi, or from r theta phi to xyz, either way, you can use the equation in the green boxes of the conversion table, which is the coordinate variable. Okay, whether you want to change from Cartesian to cylindrical or vice versa, whether you want to change from cylindrical to spherical or vice versa, or whether you want to change from spherical to Cartesian or vice versa. Use the equation in the green box. And then whenever you want to convert a vector A, okay, vector A, use the equation in red boxes of the conversion table, which is the second row here, the vector representation. Whether you want to change from Cartesian to cylindrical, or from cylindrical to spherical, or from spherical to Cartesian, or vice versa. So remember again, if you want to change the coordinates, you use the one in green boxes. So here, if you want to change Cartesian to cylindrical, use the one in the green boxes. The r would be equal to square root of x squared plus y squared. And then phi is equal to the inverse of tan y over x, and z would remain the same. But if you want to change cylindrical to Cartesian, you want to achieve x, y, z. So x would be equal to r cos phi, y would be equal to r sin phi, and z would remain the same. So next one, you have Cartesian to spherical. So meaning that you are trying to change from x, y, z to r, theta, and phi. And then from spherical to Cartesian, meaning that you are trying to change from r, theta, and phi to x, y, z. So the one in the green boxes here is when you want to change the coordinates. And then the one in the red boxes here is when you want to change the magnitude. So you see here that you're trying to change to spherical. So that's why you have AR, A theta, and A phi. And the one over here, because you are trying to change it from spherical to Cartesian, that's why you are trying to get AX, AY, and AZ. And finally, when you want to change from cylindrical to spherical, okay, so spherical, you are trying to get the R, theta, and phi, okay. So the one in the green boxes is that when you are trying to change the coordinates. And then the one in the red boxes is when you try to change its vector, which is AR, A theta, and A phi. So here you have spherical to cylindrical. So cylindrical would consist of R, phi, and Z. So the one in the green boxes is when you're trying to change the coordinate. And the one in the red boxes is when you are trying to change its vector. So here in example 1.5a, you are given point P1, 3 minus 4 and 3. And vector is equal to 2x hat minus 3y hat plus 4z hat. So this, when you see x, y, z, immediately you will know this is the Cartesian coordinate system. So the question asks you to express P1 and also its magnitude in cylindrical coordinates. So you have to change from Cartesian to cylindrical and evaluate A at P1. So which table that you have to refer to? It is the Cartesian to cylindrical coordinate table, which is this one. So you have to change from Cartesian to cylindrical for the coordinates in the green table, in the green box here, and then the magnitude in the red box.